I'll speak in English, even though I do understand Russian. You can ask me questions later in Russian if you prefer, but it's a lot easier for me to give technical talks in English. So before we start, I just want to say an amazing thank you to the organizers who brought us here. It's been a great holiday. I've been here since Wednesday, and yesterday Mshina Времени were just happening to be here, and we couldn't possibly miss it. And so this is me over there, somewhere. I think it's me. I'm not actually very sure. There were a lot of bald people, but I think it's my shining bald head over there. Yeah, so thanks a lot for coming, and this is going to be the Performance Investigators field guide. As you might know, if you've heard any of my talks or read my blog maybe or Twitter, I do performance investigations as part of my job. I work as a consultant and trainer, and so a large part of what I do is solve issues for customers or try to sort of guide them into solving performance problems and debugging things. And a set of thoughts and guidelines emerged from this work that I've been doing over the last 12 years or so. I work for an Israeli training and consulting company called Sela, and again, that's kind of my day job, so I'm just here to tell you a little about it. So I want to share with you my strategy, my tactics for solving performance issues in the field. And there's a few things I hope you'll be able to learn, which is what a performance investigation looks like. So how do you approach this thing in a methodical way? Some methods and anti-patterns for doing a performance investigation. A little tools, even though I'm not going to talk a lot about tools. There's other sessions today that are going to be a lot more hardcore, I think, in terms of tools, but we'll talk about them a little. And how to avoid getting lied to by the tools. So how to avoid getting the tools giving you the wrong information. So here's the structure of a performance investigation the way I see it. You have to start with a apparently trivial thing, getting the problem description, which is, as you probably know as developers, not always that easy, just to understand what's wrong, but just to understand what they are expecting you to do, your users, your managers, your customers, what exactly the problem is. Then what I do is try and build a system diagram. So, you know, which components are there, their interactions, who's talking to whom. I want to run a quick performance checklist to get a general idea of what's happening on that system, which components are loaded, which are overloaded, which resources are used in different ways. I want to understand which component is likely showing the problem. And then, that's the interesting part, you want to investigate thoroughly and try and figure out really what's wrong with that part of the system that's not working. And then you find the root cause, which is the thing that you have to fix in order to remove the problem from your life, resolve the issue. You want to verify that you solved the problem, that after removing that root cause, everything is now working properly. And you want to do a post-mortem. You want to document what you did. You want to make sure it's not going to happen again. And if it does, you want to have a very clear set of steps in order to repeat the solution you just found. So that all obviously sounds a lot easier than it is. And if you've done performance work or if you've done some hard debugging, you know it's all really nice in theory, but it's not as clean and nice in the real world. So I'm going to talk about a couple of examples as well a little later. So I'm going to start with some examples of problem descriptions, good and bad. So here's a typical problem description that I get a lot. The application feels slow. The users don't really know what's wrong, but it feels slow. So please solve the problem. It's hard to work with this kind of problem report. Here's another example, which we get a lot as a consulting company. So we have a 2-day budget to bring a consultant, look at our system, and solve our performance problems. That also happens sometimes. This is kind of workable because at least they give you like a free hand at solving whatever you want, but it's not usually very productive. Slightly more productive, here's a typical problem report from an automated system, maybe some monitoring system that you have. Since 4:25 a.m., performance has degraded. The 95th percentile, and we'll talk about percentiles a little later, has gone up to 1400 milliseconds, and it was 60 milliseconds before. It has been that way since, and we tried some things to solve it, but it didn't help. So this is the thing we want you to focus on. We need to bring the response time down for that ASP.NET application. That's a reasonably good error report. Another example from a customer-facing, maybe a UI app in a hospital. So in the latest beta, clicking from the patient details to the CT screen in this medical application takes 11 seconds. And that is unacceptable. It should take less than 2 seconds, or doctors and hospital personnel just can't work effectively. So you need to bring down, again, the transition from one screen to another. You need to bring that down under 2 seconds, because that's what it was before. So these are actionable problem reports. You know what you're trying to optimize. You know what the criteria for success is going to be. You know when the customer is going to be happy. And even if you're not working as a consultant, even if you're basically solving your own performance problems, it's still good to have a clear definition of what it is you are trying to solve. So let's talk about these requirements a bit, just, you know, what exactly we're trying to optimize, and what the optimum should be, and what's acceptable and what's not. So this is a typical conversation performance consultants often have with their customers. So I ask, what are your latency requirements for your system? Maybe a web application, maybe a GUI application, doesn't matter. The customer says, we need an average response time of 20 milliseconds. Okay, well, what is the worst case then? So 20 milliseconds is the average. What is the worst case requirement? The answer is, we don't have a worst case requirement. We didn't think about it yet. So I ask, can some requests take more than 5 minutes? Because you can still have an average of 20 milliseconds, but a worst case of 5 minutes. So of course not. Nothing can be ever worse than 100 milliseconds. But that's a little ambitious, isn't it? Even if it's just 2 requests per day, you still can't go above 100 milliseconds? Okay, well, you can go over 100 milliseconds, but you can't go over 2 seconds. So that's like the worst case I'm willing to accept. So how often is a 500 millisecond response time acceptable? Because I can give you 96% 1 millisecond response time, and then 4% 500 millisecond response time. And that works out to a 21 millisecond average, which is what you asked for, but 4% of your users are getting half-second response times, which is probably really horrible. And at that point, the conversation often stops. But it's important to have an idea of really not just the average of what you're trying to monitor and measure. It's good to have an idea of what the worst case is, how many customers you're willing to subject to the worst case experience. So is it okay that 1% of the customers are having that worst case experience? Is it okay for 5% of the customers to have that worst case experience? It really does matter. And ideally, all these metrics that you have come up with are expressed somewhere, are written down somewhere, and agreed upon by not just us developers and performance engineers, but by the business people as well. So they are derived from business metrics, they are derived from customer interactions, they are derived from what your marketing has promised customers you will deliver. And if you have this kind of agreement with your customers, they're going to be a lot more understanding if they do get the occasional slow response. They know it's within your SLA. So that's a totally different discussion. We're not going to talk about SLAs here. But of course, once you have these numbers, once you have these performance objectives, you want to monitor them automatically so you know when you have a problem before someone comes and starts knocking at your door at 3 a.m. So let's talk about the actual investigation then. We have those performance objectives, we have an idea of what the steps are, so let's take a look at some of the ways to conduct a performance investigation. And here are some anti-patterns, anti-methods, things you shouldn't be doing. I've gathered 5 examples, but there's a lot more. You know, there's a lot of ways to do something wrong, and there's not a lot of ways to do something right. There's got to be a proverb about this. So the number one mistake all of us do as humans is probably make assumptions. We kind of have an intuition of what's wrong, and sometimes it's a really great intuition, but other times it's not really related to what's really happening in our system. And if we don't have good metrics and monitoring, if we don't have good insight into the various pieces of our system, the intuition just sucks and you can throw it away. Trusting instincts and various irrational beliefs is also a bad thing. Like, you know, having this idea of how something works, which isn't really right or isn't really up to date anymore. Looking under the streetlight, I'll talk about this a little later. What I mean by that is that you look where it's easy for you to look. So you have this huge system, a lot of things could go wrong, but you have good visibility into 1% of your system. So that's where you're focusing your whole performance investigation. Usually not a good idea unless the problem is really there. Using random tools, I'll talk about that later. And blaming the tools is another common mistake. So let's talk about the common mistakes first, and then I'll talk a little about ways to do things right. So this is a story of how I failed to do a performance investigation for a customer. It was partly my fault, it was partly other people's fault. I'm not assigning blame here, just trying to tell you a story where we can learn from mistakes. So I had a customer with a document management system. Just, you know, loading documents, saving documents, some network storage, that sort of thing. That's what they had. It was built in-house. And we had certain kinds of operation cause a timeout. So loading documents and saving documents would sometimes cause a timeout, and the end user would actually get an error, and they would have to reopen the document, retry. It was a really sucky experience for them. And the whole document storage system was on a NetApp appliance. I don't know if you've worked with NetApp before or if you will in the future. It's a storage system like a lot of others, and it kind of works, but it's a black box in a lot of organizations. It's something you need a dedicated administrator to look after. You can't just get, you know, ordinary people like you and I to work with NetApp. You need dedicated, trained engineers. So this is the general architecture, not really super interesting. We have clients connecting over WCF to some kind of application server, and that application server is accessing a NetApp storage appliance, which is where the documents are. So we had a lot of performance tools we could deploy, look at the server, look at the clients, look at the network. The one thing I didn't really have a lot of visibility into was that NetApp storage appliance, because I was not the engineer allowed to touch the NetApp storage appliance. So again, a few emails exchanged between the different parties. So after looking at a lot of network traces, I said, it seems that the average time to access documents on that network storage appliance was 11 milliseconds, but we have worst cases of more than 1 second. So sometimes it takes more than 1 second to access documents on that remote storage appliance. So I asked for network traces, and I asked for performance counters from the storage appliance itself, which again, I didn't have direct access to. So I got the network traces. The network engineers were really cooperative, and the network traces say that the worst case network latency was just 10 milliseconds. So again, if we go back to this beautiful diagram, it kind of shows that the network is working really great, and it's a local network, it's really fast, but it still seems that some storage operations are taking longer than a second. So we don't know where this is coming from. And of course, I suspected it was the storage appliance. So they had to bring in a NetApp consultant, because again, you can't just look at NetApp appliances yourself, you need to bring in an expert. So the NetApp consultant will come next week, but in the meantime, we have our local NetApp administrator, and they said that the NetApp latency is always under 5 microseconds. So there's no way it's the storage problem, because 5 microseconds and any document, regardless of its size, 5 microseconds, we can load that document all the way up to you. The NetApp consultant came in the next week, and they said it's not really 5 microseconds, it's really 5 milliseconds. But, I mean, it's almost the same thing, and under 5 milliseconds, that's the performance of the NetApp appliance. So here we're coming to the interesting part. What is this number? What does it mean? What is this 5 milliseconds? So I asked a very simple, I thought, question. Is that the average or the worst case? Because I know I have a worst case problem. I don't have an average case problem. So is that number the average or the worst case? They replied, it's the maximum average value over 60-second intervals. I've given this talk before, and I still read this sentence and I don't know what it means. So it is a maximum average value over 60-second intervals. I've had some conversations on Twitter about this with people, and they were trying to convince me, no, this is a meaningful thing. It means something. You just don't understand what it means, but it means something. Maybe it does. But I don't know if it's like you take all the averages and then you do a maximum, or maybe you take all the maximums and then you do an average. It's not the same thing. And then what is this 60-second interval? Do you take 60 measurements and do an average? Or do you do an average over the whole minute and then you do a maximum of all the minutes? I don't know. Yeah, so that's what we got. At which point, I looked it up online. And I found this beautiful table from the NetApp documentation that has a list of all the different performance counters you can get from the NetApp storage. And there's stuff like read latency and write latency, and it's at a second resolution. So it's not like each individual operation, but at least it's not the maximum average value of 60-second intervals, whatever that means. Unfortunately, they ran out of budget to bring the NetApp consultant again. And so to this day, we do not know what the worst case storage latency was for that NetApp appliance. And this is, even though it's like a really bad story and it doesn't really give you any tools to do anything, it is very typical, unfortunately, in a lot of ways. It's typical in how people kind of just assume things. It's typical in how people mean different things when they communicate. So for one person, an average is this, and for another person, an average is that. It's interesting in how organizations and bureaucracies work. So there's a lot of things to learn from this, even if it's not really how to actually approach performance investigations. Yeah. So I hope this showed you a couple of examples of bad things to do along the way. I want to show you real quick 3 other tiny examples of other anti-patterns, and then we'll talk a little about performance investigations done the right way, or some methodical approaches for looking at systems performance the right way. So one common thing a lot of developers do, this often happens before production, just in development time. I have a little time on my hands, and I have an expensive CPU profiler that my boss has just purchased. So let's run this expensive profiler and see what it says. And that's, I mean, it's nice. Yeah, it's definitely better than not doing any performance investigation, but it's important to understand that different profilers measure different things. And a lot of CPU profilers, they really just measure CPU. They don't look at anything else. They don't look at network wait time, they don't look at database accesses, they don't look at file accesses, they only look at CPU time, computations, you know, instructions, churning numbers, back and forth. And so if you look at a report from a CPU profiler, when the application is not actually doing that much CPU work, you will get totally meaningless results. Like in this example, I wrote a little application that downloads web pages, just has a list of web pages, and it goes and downloads every page, and then it prints some statistics. And the profiler says the printing is the heavy part. Like console.writeLine is the most expensive thing this application is doing. And it's probably not. I mean, like most of the time, this application is waiting for the network, waiting for HTTP responses to come back, but it's not CPU work. So a CPU profiler will not be the right tool for the job. So this is looking under the streetlight or just using the tools you have at hand without really understanding what your situation is specifically. Just a tiny example of how that can happen. Another example is using, again, the wrong tools or not really understanding the tools you use. So this is just the console application that I have as part of my training. And if you look at it in Task Manager, it says it's using only 10 megabytes of memory, but it crashes with an out-of-memory exception. So, I mean, it's only using 10 megabytes of memory, and it crashes with an out-of-memory exception. Clearly, something is wrong with the tool, or clearly there's not really an out-of-memory error. Maybe it's a bug in the CLR or something. So you can definitely go that way. And Task Manager doesn't really help. By default, it just displays, as you might know, private working set. That's the metric it displays. And private working set for a process is private memory, which is not shared with other processes, so it doesn't take into account any shared memory. And working set means memory that's currently in RAM, in physical memory. So it doesn't account for anything that's not in physical memory right now. Any virtual memory that's backed by the page file or memory mapped files or that kind of thing. So yeah, this application might only be using 10 megabytes of private working set, and it still might be out of memory because private working set is not the whole thing. But I mean, I can definitely imagine an administrator look at Task Manager and be surprised here. Like, how come this app is out of memory when it's only using 10 megabytes of memory? So again, using the wrong tool or not really understanding what the tool is showing you is a very typical thing that happens in performance investigations, unfortunately. And one final example from not really understanding the tools, again, super simple. Like here's an application you are all probably familiar with. This is Notepad. And this is a tool from sysinternals called VMMap. And VMMap reports that this application is using a total of, so this is 2 terabytes, just a little more than 2 terabytes of memory. It's really hard to get Notepad to actually use 2 terabytes of memory. Like, what do I have, like a huge file I've just opened up in Notepad? And so you might conclude, again, the tool is wrong, or maybe there's a bug in Windows or something. Again, unless you know what this number really means, and I'm not going to give you the whole internal details, but generally speaking, there is a Windows feature in recent Windows versions that reserves a lot of address space for security purposes, and that memory reservation is not really physical memory, it's not really disk space, it's just an address reservation. For 64-bit processes, you have a lot of address space you can reserve, and so this Notepad is not really using 2 terabytes of memory, but that's what the tool just seems to suggest, if you don't know what it really means. So just a few examples of anti-patterns and things going wrong in a performance investigation. And let's talk a little about maybe the right way of doing things. And there's a lot of methodologies for doing performance investigations. They're all fairly similar in that they try to look at the whole system, isolate the problematic component, and then put all your effort on that problematic component. And one approach is called USE. It's popularized by Brendan Gregg, who's a great performance architect working mostly in the Linux world. He's at Netflix right now. And USE stands for utilization, saturation, and errors. So for each resource in your system, you want to know these three things: utilization, saturation, and errors. So what does it really mean? What is saturation? What is utilization? And so on. Utilization is a metric of load, so how loaded that resource is. Saturation is a metric of overloading or queuing. Do you have anything that needs that resource but can't get that resource right now? So do you have queuing for that resource? And errors are just errors. Do you have exceptions, errors, faults, failures in that resource? Now, an easy way to get this into your toolbox is to have a diagram. And so here's a diagram for hardware. So you have a CPU, you have memory, you have a disk, you have a network adapter. For each of these things, you can look at utilization, saturation, and errors. And usually, for hardware, these things are really easy to get because there's a lot of monitoring solutions which can tell you your CPU utilization or your memory utilization or your disk utilization. These are very standard things to look for. You can do the same thing with software. So in software, you might have various kinds of microservices and databases and web caches and web applications and load balancers. And all of these things, again, have utilization, saturation, and errors. So you can look at all these things and, again, measure utilization, saturation, and errors. And you should also look at the connections between them. It's not always the web server that's loaded or overloaded. It might be the queue from the load balancer, or it might be the down queue to your database. Queuing is also important, and you have to look at queues and connections between resources as well. So once you have this diagram of your system, and you have a way of monitoring utilization, saturation, and errors, you should be able to have this kind of checklist, a list of things to monitor, hopefully automatically, so you can get alerts, and so you can easily zoom in on the component of your system that's really exhibiting the problem. I have on the slides, which you will have later as well, a list of some of the ways to monitor CPU utilization, memory utilization, network utilization. You don't need to take pictures of this because I'll have the slides for you later. So these are easy ways to monitor the hardware resources, and similar approaches exist for software as well. And then again, you want to monitor these things automatically, and there's a lot of solutions for this. So an easy option, if you're really not using any third-party software, is just using the Windows Performance Counters infrastructure. So you have tools like TypePerf, which can monitor these metrics and dump them out to the terminal. And of course, there's again a lot of third-party software that will happily monitor these numbers for you and let you zoom in on the resource you have to focus on. So I want to share with you another performance investigation story. This one is really old. The previous one was from like early last year. This one is from 2009. And it's a story of how we found a bug in the garbage collector in CLR 2.0. Now, I know it sounds suspicious that someone found a bug in the CLR garbage collector. It sounds like an excuse. Like, I don't know what the problem is, so the problem is in the garbage collector. But this was really a bug in the garbage collector. So let me share you this quick story with you. We were building a network processing system that basically reads a lot of packets and tries to parse them. So most of the packets are not really interesting. So we just look at the header and we throw that thing away. But there are some packets that are interesting, and we want to look at the content really closely and maybe save them somewhere. So we need to process certain packets really carefully. And so we looked at the logs. And we had those weird, I'm going to call them hiccups, these weird delays where all of a sudden the system would freeze for half a second, a whole second, 3/4 of a second, and then just keep working as normal, as usual. And we could even see this in the logs. So starting to do something with a packet, and then bang, 500 milliseconds of no messages in the log, and then everything comes back again, and yeah, okay, we're working, we're processing, we're fine. So that was the way it looked on the logs. Looking at some specific performance numbers, we were able to come to this chart. It was a lot harder in 2009 than it is today, but still. And this shows two metrics. The blue line is the number of packets processed per millisecond. So it's like several tens of thousands of packets per second, really. And the red line is CPU utilization. So, you know, everything looks perfectly fine and normal. And then there's two weird phenomena here. The first drop over here, we are still working, we're still processing some packets, okay? So it's not a complete drop to 0 packets, but we're still processing, it's a lot slower though. And CPU utilization is also dropping, it's also slower. And then there's a complete halt in packet processing. So this is the really suspicious part. 0 packets being processed, but CPU utilization goes to 100%. And then everything comes back to normal with a little more JIT because we're recovering, but generally everything comes back to the same median load, and we're working again for a few seconds, minutes, hours before we hit the same scenario again. Now, a lot of you are thinking at this point it has to do with GC, because the GC is probably the only thing that can introduce this weird, unexplained pauses into your application. Just stop everything for a little while and then let everything resume as normal. And so my suspicion, of course, was also that the garbage collection had to do with this. And here's another funny thing that the engineers have noticed, which makes it a little weirder, and it's the pauses were always close to a multiple of 250 milliseconds. So it was like 252, 503, 751. It was never just a completely random number, it was always these multiples of 250. Now try to explain that with your garbage collection theory. The garbage collector is not that deterministic, it would always take multiples of 250 milliseconds to do something. Okay, so I asked for garbage collection information. I'm going to skip ahead a little bit. And at some point we realized we can't really progress without looking at what the threads are doing during those hiccups. So we had to build a whole infrastructure that would allow us to attach a debugger at exactly the right time when these hiccups were happening and grab stack traces. It's a lot easier to do in 2017 than it was in 2009. So again, forgive us for taking so long to get there. But once we did, these are the thread stacks that we saw. And just to give you a really quick picture, if you can't see everything from the back of the stage, we have 4 GC threads not doing anything. They're not doing GC right now. They're waiting for the GC event to arrive. So they're only waiting for a notification to start collection. No collection currently happening. And then we have 2 application threads. One application thread is parsing packets, super busy, working happily, processing packets. The other application thread has hit an allocation cap. It is trying to allocate, but it can't, so it needs a garbage collection to occur. So it's trying to do something called suspend EE. It's trying to suspend this thread so that these threads can start doing garbage collection. It's a little complicated, right? So we have this thread failing to allocate, trying to suspend this thread so that the GC threads can start the garbage collection. And that was always happening. And we did disassemble a little of the GC code. Today it's open source, so we could have looked up on GitHub what it's doing. Back then, again, it wasn't open source. So we disassembled a little, and we found this is what the suspension code basically looks like. So as long as the GC suspension was not successful, and as long as we haven't given up yet, we wait for 250 milliseconds to see if the GC suspension is going to succeed. And then when we return, we check again, is the GC suspension complete? If yes, we get out. If no, we just keep trying for 250 milliseconds. There's two ways to get out of this loop. One is if we succeed with the suspension, so we manage to stop the other thread. The other way out is if we give up. I haven't really figured out the whole give up condition exactly, but that's what was happening in our situation. We were never successful at stopping the other thread. We were always just giving up on the suspension and moving on to this part, which calls suspend thread non-cooperatively, just stopping that thread, whatever it's doing right now. So this is the scenario we had. I didn't really know what to do with this information. I found a workaround where changing the code a little bit stopped this issue from happening, just basically introducing a few lines, introducing a sleep here and there, just sort of got this issue out of our task board. But a little while later, I posted this on my blog. And in 2009, again, it wasn't that easy to get to Microsoft performance engineers and get them to look at an issue like that firsthand. So I just posted it on my blog and forgot about it. And a little later, the lead engineer for the garbage collector at Microsoft reached out and posted a comment. And the last part of the comment was, I ran your repro and I do see the suspension problem. We'll take a look. And a few months later, we had a hotfix. So it was indeed a bug in the suspension engine of the CLR where it would fail to suspend a thread under certain conditions and just keep trying with these 250 millisecond intervals. And today, the whole cycle could probably have been 3 days and not 3 months or 6 months, because we have the source code, we have a lot more access to the relevant engineers, we could debug into the CLR and see what's happening, we could maybe even fix the bug if we had sufficient resources. It was all a little harder back then, so I hope you are delighted that you are .NET developers in 2017. So anyway, that was the story of one performance investigation from back then. You can find all the details on my blog later if you'd like. So moving on, I want to talk briefly about qualities of good performance tools. What good performance tools look like, what I look for in my tools, and how sometimes performance tools just kind of suck and lie to you. So there's 3 kinds of tools, if you think about it, that all of us use for performance investigations. One is a counting tool. How often is this happening? How many packets per second? How many requests per minute? That kind of thing. The other is latency tools. How much time is this taking? And the third kind is stack-based tools. So what is causing this thing to happen? What is the stack trace in my application which is leading up to that thing that is happening? And regardless of what kind of tool you use, here are 5 qualities of good performance tools that I believe you have to think about when choosing a tool. So the first one is low overhead. You want to use a tool that doesn't affect your performance too much, because otherwise you're basically measuring the tool and not really using the tool to measure your system. The other quality is accuracy. It's kind of obvious, but tools need to be accurate. Tools need to report accurate information. I'll have a little story about this in a moment. The third point is quick turnaround. You want to be able to get information quickly. You don't want to wait 3 hours to get a report. That's not really useful. You want the tools to be production ready, by which I mean you can run them in production. You don't have to restart your whole system to run a performance tool, or you don't have to inject code into your system to run a performance tool. And finally, by focusable, I mean the tool lets you zoom in and find the area in your code, the area in your system that you really should be looking at. So I don't have time to actually show you specific tools and specific scenarios, but I do want to show you a couple of examples of how these things can go wrong. So first, in terms of accuracy, I don't know if any of you are doing Java profiling work as well, but if you are, most Java profilers people use today, including commercial profilers, basically lie to you because they use a really flawed way of getting performance information out of the system. They stop all threads to see what they're doing a certain number of times per second, but the way they stop the thread introduces bias. So the thread isn't stopped whenever it is, it's only stopped where it reaches a certain safe point. So basically there are pieces of Java code you will never see in a performance profile if you use tools like that. And there's interesting research, which I really encourage you to look at later, that shows 4 different profilers giving you completely different information about the exact same program. So one profiler says this method is most expensive, the other profiler says no, that method wasn't even running, that method is most expensive, and 4 profilers give completely different results. It's really phenomenal how even today performance tools can be so bad in a way. For .NET profilers, there's a lot less of this stuff. But still it's possible that your profiler is giving you inaccurate information. So unfortunately, when you introduce a new tool into your system, you have to check the tool. You have to test the profiler first, especially if it's something new or something a lot of people haven't used before. Another point is invasiveness. A lot of profilers are really invasive in the way they work. They inject themselves into your system. Just a couple of examples. The Visual Studio Profiler has a mode where it has to change your bytecode, change your IL, in order to profile the application. IntelliTrace, if you've used it, is either based on breakpoints, which is super expensive, or IL instrumentation again. So a lot of profiling tools, if you check the documentation, you'll see they're really, really invasive in the way they work. And there are, of course, good performance tools as well. There are good tools like ETW, for example. I'm not going to show you a lot of examples because, again, we don't have a lot of time. But ETW is something all of us .NET developers should be familiar with in 2017. Event Tracing for Windows is a performance monitoring framework built into the operating system that you can use non-invasively in production to monitor CPU performance, disk performance, garbage collection performance, and a lot of other interesting events. And while we're talking about ETW, I want to come back to that point about quick turnaround. So this is an example of recording ETW on one of my production systems. I recorded 10 seconds of information, a 10-second trace, and that produced 15 megabytes of data. That's kind of scary, isn't it, if you want to run this continuously in production. But also, you'll notice it takes a long time. It takes 12 seconds to process the trace, another 4 seconds to convert it, another 4 seconds to open it, and, oh well, a little less than 250 milliseconds to do even something else while opening it. So the turnaround here is slow. To record and open a 10-second trace, you probably have to spend a minute or 2 after you stop recording. This is, I think, unacceptable. And so the last thing I want to tell you about is that I've actually written a couple of tools because I couldn't use the default ETW workflow anymore. And so the couple of tools I'd like you to look at perhaps later is eTrace, which is an open source tool for command line ETW tracing, where you can ask to trace garbage collections, process events, file events, and just get output in your terminal. And the other tiny tool is called Live Stacks, which you can look at later as well, which does stack aggregation. So show me all the stacks causing garbage collections, show me all the stacks causing file accesses, or that sort of thing. And again, you'd get output in your terminal. So we're pretty much out of time, I believe. And so I'm just going to skip over to the end to show you just this little summary. I hoped to show you what a performance investigation looks like. I wanted to show you some of the ways things can go wrong along the way, some mistakes a lot of people make, and some ways to get over them and methodically approach a performance investigation. A little overview of tools, and again, good qualities of performance tools, because there's lots and lots of profilers and performance tools available for .NET today, and how to avoid getting lied to by inaccurate tools and other mistakes. You can find the slides here and some references as well. I hope you enjoy the rest of the day. Thank you very, very much.
So now we have time for several questions. So if any.
Yeah.
By the way, we have nice presents for those who
We do have presents.
Yeah.
Thank you, Sasha. I actually heard these reports during your St. Petersburg.
Oh, okay.
But yeah, I didn't ask that question that time. You said SLA is kind of out of the scope. Still, I want to return to it a bit. When you said you have a long conversation with your customers regarding how fast it should work and everything, do you provide any recommendations to them? I mean, there are a lot of studies, like psychological stuff and everything, regarding what seems to be fast to end users, what seems to be slow, what seems to be unacceptable. Do you rely on them, or do you usually wait for the customers to provide you exact figures?
So yeah, I mean, there's a lot of research for customer-facing applications, like where the user has to wait for something or the user has to interact with the system. There's a lot of research on what is acceptable, what the user is willing to tolerate, and also how to hide bad performance. Like if you completely freeze the screen, that's one thing. If you show a progress bar, that's another thing. If you provide something useful and then the whole picture a little later, that's a different thing. So yeah, there's a lot of research on that. I usually don't participate in that phase where we try to establish a good UX for the interaction with the application. So that's not really my area. But in general, when it comes to establishing objectives, performance objectives for your system, I mean, it's something there's definitely a lot of research on. I think in terms of books, one great book is the SRE book by Google, which covers establishing service level objectives for your services, which I guess you can extrapolate to end users as well. So how do you establish objectives for what your users are going to see also? And sometimes it's also just, I mean, sometimes the point where I get called to the customer is so late in the process where we can't really change what the original design is or change the objectives. We can just establish what the system is capable of providing, and then I make sure we can at least meet that goal, or maybe improve it a little, but not really, go back and think how to build the whole thing in the first place to be exactly what we wanted. So it's mostly, I guess, like remediation and not upfront planning. That's just the nature of my work. I mean, I bet there's a lot of people who do the upfront performance planning a lot better than I, because I just usually come in at a lot later point. Yeah.
Thank you, Sasha, for a great presentation. I have a question regarding systems that you cannot touch. For example, we have some applications that go to production. It's a big internal network. We have no access. We cannot install tools, but customers blame tools that it's slow. So maybe you can advise how to deal with such kind of situation when you cannot do a lot.
Yeah.
Thank you.
So, I mean, I assume it's Windows, and then Windows has a lot of built-in stuff that you don't need external tools for. Like ETW, one of the key advantages is that it's built into the system, and to record ETW, you don't need to install any additional tools. So you can give your customers like a tiny script which they can run, or even manually, if they can't even run a script, you can give them instructions like click here and there and there and there, and that would give you a recording that you could analyze. Assuming that you can extract that recording from the internal system and eventually get it to your environment. If you can't, I mean, there's not a lot you can do, but right? If you can't install any tools, if you can't run any tools, and if you can't get any information out of the system, there's not a lot you can do. But ETW works really well when it's a very constrained environment and they don't let you install. Yeah, and they don't let you install anything. ETW is really fantastic for getting at least a minimal recording of what's happening, and you don't need any tools for that, any additional tools in it.
Yeah. So we have time for the last question.
Okay, thank you. What about black box and cloud, something like this? Maybe some part of application hosted on cloud, but you don't have any access to this part. What pattern of your work in this case?
So you're asking what monitoring tools can be used in the cloud? Yeah, so if it's, it depends on what kind of managed infrastructure you're using. If you are just running VMs in the cloud, then obviously you can put whatever you want on those VMs and just, same as on premises. If it's a more managed offering where you don't have like remote desktop to the system, or if you can't run background processes at all, you only have this main process that has to do all the monitoring internally, it definitely limits your options, but still a lot of things can be done. Like again, ETW, you can record it programmatically from within the same process. There's a lot of third-party monitoring solutions for specific kinds of applications, like for ASP.NET, there's a lot of tools that would inject themselves in the ASP.NET pipeline, so to give you statistics on request execution, which controllers are working a lot, database queries, that kind of thing. So you'd be looking at more invasive things because you can't just look at the system as a black box. You do have to come in to get anything. But yeah, there's definitely options there. Most cloud providers also have like built-in monitoring solutions, like Azure has application insights, obviously, and other platforms have their own stuff as well. But I mean, it's of course depends on your runtime, right? If you run .NET on Azure, you might get better monitoring options than if you run .NET on Google Cloud Platform, maybe. But it's definitely possible. Sometimes there are tools that won't work, or you just can't even put the tool in your system to run it, but it doesn't mean you can't do performance investigations.
Okay, thank you. Could you please select the best question?
Yeah, no, there were all good questions. So can you just give 3 presents to everyone?
Okay. So maybe the first one. Okay. Thank you.
Yeah, I'll be here during the rest of the day if you'd like to talk to me about anything. Thank you very much. Yeah.
Thank you.